We are in chapter 2 where we are discussing strain. This is the 10th session overall and the second session involving strain. Here we discuss Poisson's ratio, generalized Hooke's law, shear strain, among other things. Also, a summary of the discussion on strain is given at the end. This map gives us a glimpse of where we are in the overall context. We are in chapter 2 and in second session where we discuss strain and the relationship between strain and stress. We now discuss Poisson's ratio. To start with, we remind ourselves that we are dealing with a material that is homogeneous and isotropic when we consider bodies. We earlier briefly mentioned that when a bar is subjected to axial loads, there is a contraction in the lateral direction. So the lateral cross-section reduces in area in the case of a tensile load acting. In the case of a compressive axial loads, there would be an increase in the cross-sectional area. The ratio of increase or decrease in length in the lateral direction to the original length in the lateral direction is called the lateral strain. Lateral strain is positive when the body expands and negative when the body contracts. So here, to which an axial load has been applied. The load is tensile. The original is shown in dotted line. So this is the body without any application of loads. After application of loads, the length of the body has increased in the direction of the load. However, the cross-section has contracted. The contraction here is shown in an exaggerated manner. Now we have talked about lateral strain and axial strain, and it has been found that the ratio of the lateral strain to axial strain is constant for a given material. The negative of the lateral strain to the axial strain is denoted as nu. Nu, like the Young's modulus, is a material property. It generally varies between 0.2 to 0.35. Nu is always positive. Say if there is a tensile load acting on the body, then axial strain would be positive, but lateral strain would be negative. So nu would be positive. Say a compressive load is acting on a body, then axial strain would be negative, but lateral strain would be positive. So again, nu would be positive. So nu is given as minus epsilon y divided by epsilon x is equal to minus epsilon z divided by epsilon x, because the body is isotropic, or the material of the body is isotropic. Now the lateral strain can be given from the axial strain. So here epsilon y is equal to epsilon z is equal to minus nu into epsilon x, where epsilon x is the axial strain. So the lateral strain is given from the axial strain by multiplying by nu. Here we discuss generalized Hooke's law. Till now, we have dealt with cases where load is applied in only one axial direction. The discussion on Poisson's ratio also involved in one direction only. The contraction or expansion in the lateral direction was determined. Here we will consider load being applied in three perpendicular directions along the three axes. Hence, normal stresses will act along the three perpendicular directions. Only normal strains will be caused. It is an experimental known fact that normal stresses cause normal strain and shear stresses cause shear strain only. It is considered that the loads applied will be within the proportional range. Hence, Hooke's law can be applied. Also, the stress-strain curve being linear, the strains can be added together. Let us consider this body. Normal stresses has been applied in three perpendicular directions. Here, three cases are shown where stresses have been applied in one direction only. So here, due to tensile stress sigma x, there will be extension in the x direction and contraction in the y and z direction. In this case, there would be extension in the z direction and contraction in the x and y direction. Similarly with this case. Now let us discuss the case where we look at strain in x direction only. Now strain in x direction for this case epsilon x. Strain for this case in the x direction would be nu into epsilon z. Strain in the x direction for this case would be nu into epsilon y. These two cases, the strain in x directions are contraction. So the total strain in the x direction will be given as epsilon x minus nu epsilon z minus nu epsilon y. Hence, if the total strain in the x direction is epsilon x dash, then epsilon x can be written as sigma x by E minus nu. Epsilon y can be written as sigma y by E, and similar with z. We can find the strain, the total strain in the other two direction. So epsilon y dash would be given by epsilon y minus nu epsilon x minus nu epsilon z, and similarly with the z direction. If all three forces were compressive, and the stresses obviously would be compressive, then this would be compression and these two would be expansion. So there would be change in signs in all three. Here we discuss shearing strain. Earlier we had discussed the state of stress at a point in a body subjected to loads, the reference to a coordinate axis. The state of stress was defined at the point on an infinitesimal cube lined with the coordinate axis. Instead of a cube, we could have used a rectangular cuboid. We discussed that in most cases, the stresses associated with the z ordinate is zero. The stresses then can be given on a square in 2 dimensions. If we had considered a rectangular cuboid, then the stresses could be given on a rectangle. Here we have considered rectangular elements. We have earlier discussed that if tau xy acts on this face upwards, then from equilibrium of forces, tau xy on the opposite face will act in the opposite direction. Also, the forces associated with these two tau xy create an anticlockwise couple. Since the element is in equilibrium, the forces associated with tau yx would create an equal and opposite couple. Tau xy acting upwards on the right-hand face is considered positive. From the discussion, we can see that shear stresses always exist as force. So there cannot be 1 or 2 shear stress. There has to be 4 shear stresses. We can also see that the arrows of the shear stresses point to the opposite ends of the diagonal or of our diagonal. We also showed that shear stress is commutative. So tau xy is equal to tau yx. Now in this element, if you remove the normal stress, we have only the shear stress acting here. This case is called a case of pure shear. We can physically see that this element with the stresses acting would deform into a rhomboid. Shear strain is the change in angle of the original right angle of the element. A reduction in angle is considered positive, as shown here, while if the angle exceeds a 90 degree, then the angle is considered, the shear strain is considered negative. In figure T has been obtained by rotating the axis in figure C so that the strain is on one side. We earlier discussed that the normal stress strain curve is linear under low loads. Similarly, the shear stress and shear strain curve is linear under low loads. The modulus slope of the curve is denoted by G. G is the modulus of rigidity and is a material constant. So we can write tau xy is equal to G comma xy. Considering the other planes, we can write tau yz is equal to G comma yz and tau xz is equal to G comma xz. We earlier denoted the slope of the linear portion of the normal stress to normal strain curve as the modulus of elasticity, and the slope of the linear portion of the shear stress to shear strain curve as the modulus of rigidity. Here we find a relationship between the modulus of elasticity and the modulus of rigidity. A square element here is shown in blue. Each of the sides are of length dx. A stress sigma x is applied as shown. Hence, the x direction will extend in length while the y direction will contract in length. The extension can be said as epsilon x dx. So the total length in the x direction would be 1 plus epsilon x into dx. The reduction in length in the lateral direction would be minus nu epsilon x dx. So the total length in the lateral direction would be 1 minus nu epsilon x into dx. Initially, the diagonal of the element makes an angle 45 degrees with the horizontal. But after the application of the stress, the diagonal makes a different angle, which we can denote as beta. Here in figure C, we have shifted the blue element so that the relation between the angles can be seen directly. So the initial angle was 45 degrees and now the angle is beta. We earlier discussed about the rotation of an element. So here a bar was subjected to tensile load and we took a section perpendicular to the axis of the bar. An element aligned with the perpendicular section was subjected to the stress sigma x, which was given as P divided by A. We then rotated the element and found the stresses acting corresponding to different oblique planes. So this is the case where the element has been rotated by 45 degrees and the stresses acting on the element is as shown. One can say that the term rotation is a misnomer, since in reality we are considering the same point and physically the element is not rotating. We are simply considering the stresses acting at a different angle or slope. Here is an element rotated 45 degrees. So this is the side which was the diagonal. It has an angle of 45 degrees with the horizontal. The dotted line shows the distorted element. It makes an angle beta with the horizontal. We earlier mentioned that shear strain is the change of the angle from the initial right angle. So, and shear strain is in two parts. So here the change in angle is shear strain divided by 2. So beta can be mentioned as pi by 4 minus shear strain divided by 2. Now we have obtained beta in two different ways. We'll equate the tan of beta, and from that we will find a relationship between the modulus of elasticity and rigidity. So this is the formula of tan A plus B. So we get this as the expression. The angle being small, we can replace the tan of the angle by the angle itself, which we have done here. Now tan beta from figure C is equal to 1 minus nu epsilon x by 1 plus epsilon x. Relating the two values of tan beta, we get the shear strain by this expression. Now here on the denominator, the second term can be considered to be small, and as such the shear strain can be given by this expression, where it is equal to 1 plus nu into epsilon x. Now replacing the strains by stresses, we get tau m divided by g is equal to 1 plus nu sigma x divided by E. The equation can be written in this form. Now here we have sigma x divided by tau m. Now from this figure, we see that sigma x here was p by a and tau m is 0.5 p by a. So sigma x divided by tau m would be 2. Replacing the value, we get g is equal to E divided by 2, 1 plus nu. Here we deal with bulk modulus. Previously, we have discussed the case of a bar subjected to tensile loads and found out the change in length. Under generalized Hooke's law, we considered volumes subjected to stresses along all three perpendicular axes. We found out the strains along all three perpendicular axes. Here we deal with change in volume. It is to be noted that only normal stress and normal strain cause change in volume. Shear stress and shear strain do not cause any change in volume. To start with, let us consider a unit cube which has been subjected to stresses in all three directions. As we found out earlier, its length will increase in all three directions. So its length in the x direction is 1 plus epsilon x dash. Previously it was 1 since this is a unit cube. Similarly, the dimension in the y direction is now 1 plus epsilon y dash, and the dimension in the z direction is 1 plus epsilon z dash. Here epsilon x dash not only includes the strain due to sigma x, but it also includes the lateral strain due to sigma y and sigma z. Similarly with epsilon y dash and epsilon z dash. Now the volume of this cube will be given by this expression. Before application of stresses, the volume was 1. To get the volume, you have to multiply these three portions. Considering that the product of strains is very small, so epsilon x dash into epsilon y dash will be very small. We get V as 1 plus epsilon x dash plus epsilon y dash plus epsilon z dash. Since the initial volume was 1, the change in volume is epsilon x dash plus epsilon y dash plus epsilon z dash. This change in volume of an unit cube is referred to as dilation. It is denoted by E and is an invariant. If we substitute the volume strains by stress and Young's modulus, we get E by this expression. Now in hydrostatic pressure, all three of these stresses are equal to P. Then this expression of E turns into this formula for hydrostatic pressure. We can write this formula as E is equal to P divided by K, where K is bulk's modulus, and the bulk modulus is given as E divided by 3 bracket 1 minus 2 into nu. We deal with some examples here. It is to be noted that in these examples, we have represented volume strain as epsilon x, epsilon y, and epsilon z instead of epsilon x dash, epsilon y dash, and epsilon z dash that we used in derivations. Examples here which are related to generalized Hooke's law. So this is the first example. This is a rectangular plate and it is subject to stress on all the four sides. The stresses are given, the dimensions of the plate are given, and the material properties are given. So in order to find, say, the change in length of AD, we have to use generalized Hooke's law because there's an axial change in length as well as a lateral change in length. We are asked to find the change in length of AB, AD, and AC. So we start with the change in length of AD, which will be given by epsilon y, considering this is the y direction and this is the x direction. So epsilon y is equal to sigma y divided by E minus nu sigma x by E, from which we get epsilon y. The length of this portion AD is 75 millimeters, so multiply epsilon y with that length, we get the change in length. Similarly, for the change in length in AB, we need to find out epsilon x. Epsilon x is given by this expression. We get the value of epsilon x and multiply it by the length of AB. We find the change in length of epsilon of AB. We can, since we know AD and CD, we can find the length of AC of the material that is not stressed. But now we have the length of AD after it has been stressed and length of DC after it has been stressed. So we can find the new length of the diagonal AC. So we have found here the new length of the diagonal AC, and this was the initial length before stresses were applied. Hence we find the change in length of the diagonal AC. This is the second example. This block is subjected to stress in the x direction and the y direction. But this stress in the y direction initially is not known. However, we are told that the dimension in the vertical direction does not change. So there's no strain in the vertical direction after the application of the stresses. We are asked to find the change in area of ABCD and also change in the unit volume of the block. To start with, we find out the value of sigma y. Since the strain is 0, then sigma y by E minus nu sigma x by E is 0, from which we find sigma y. Once we have found out sigma y, we know this stress, and there's no stress in the z direction. So we can find epsilon z. So once we have found epsilon z, CD multiplied by epsilon z will give us the change in length of CD. We can also find the change in length of AD. Multiplying both gives the new area of ABCD. To find the change in unit volume, we can use the equation for dilation. We know all the three stresses. So using that, we find the change in unit volume. We multiply this by the volume of this body, then we can get the total change in volume. We discussed two examples here. The first example involves shear strain and stress, and the second example involves generalized Hooke's law and dilation. We are told here the deflection of the plate on which V acts, and we are asked to find V and the dimension A. Since we are given the maximum shear stress, the maximum shear stress into the dimension of the plate in the middle give us the maximum force that can be applied. Now, in order to find dimension A, we find shear strain in two different ways. Now, if this deflection is given, the deflection divided by A would be one way of finding shear strain. The other way would be tau by G. So using this equation, we find the value of A. Now, this is the second problem. It has two parts. With the first part, there's a sigma y that is acting on the top. There's no other stresses acting. And we are asked to find the change in height and the change in volume. The change in height is straightforward since we have to find epsilon y. And once you have found that, you can multiply by the length to find the change in height. To find the change in volume, we need the change in diameter. So we can find epsilon x, which is be equal to minus nu into epsilon y. So from that, from epsilon x, we can find the change in diameter. The volume is given as pi r squared h. We can find the initial volume, and we can use the changed height and diameter to find the final volume, and then we can find the change. With this problem, the stresses have changed. So this cylinder is now subjected to hydrostatic pressure. So the pressure acts in X, Y, and Z direction. As previously, we are asked to find the change in volume and the change in height. Now, to find the change in volume, we can use the equation of dilation. So we can find E. We know the pressure, and once we have found E, we can multiply by the volume to find out the change in volume. To find the change in height, we have to find epsilon y. Now, to find epsilon y, we have to use all the three stresses, and we can find the value of epsilon y. Multiplying it by the length, we find the change in height. Here we give a summary of the treatment of strain within the linear portion of the stress-strain curve. To start with, we reiterate that normal loads do not cause shearing strain, and shear loads do not cause normal strain. So the treatment under normal loads and shear loads are essentially separate. The only relation is between E and G. We earlier discussed about normal strain using this example. A load P is applied axially to this bar. Then it has been found that delta L, the extension in length, is proportional to PL divided by A, from which we have found that stress is proportional to strain. The slope of the stress-strain curve is the modulus of elasticity, E. Hooke's law states that sigma is equal to E into epsilon. When load is applied to a bar such as shown here, then the bar undergoes a reduction in area in the lateral direction. Lateral strain is the change in length in the lateral direction compared to the original length also in the lateral direction. Axial strain and lateral strain are connected by Poisson's ratio. Poisson's ratio is the negative of the ratio of lateral strain to axial strain. Hence, for a body subjected to a load in the x direction, we get lateral strain epsilon y and epsilon z by multiplying the strain epsilon x with minus mu. Now consider the rectangular element here is subjected to shear stresses. Due to shear stresses, this element changes shape into a rhomboid. Initially, the angles of the element were all right angles, but after application of the shear stresses, the angles change. This change in angle is called shear strain. It has been found that for low loads, shear stress is proportional to shear strain. The curve is linear and the slope is referred to as the modulus of rigidity. Like normal strain, we get a relation between shear stress and shear strain. So tau is equal to G into comma. G, E and nu are related, and we have shown how this relation can be built. Now, using Hooke's law, we can find axial extension or reduction. The modulus of elasticity predicts the material behavior, and knowing the stress acting on a bar and the length, we can predict the extension or the reduction in length of the bar. We also consider loading in 3 perpendicular directions. The understanding of axial strain and lateral strain is used here. Consider epsilon x dash is a strain in the x direction for this case. When it is given as axial strain in the x direction minus nu epsilon y minus nu epsilon z. The last two terms are lateral strains due to stresses applied in the y and the z direction. Writing this expression in terms of sigma and E, we get this new formula. After axial stress and strain, we discussed axial extension. Here we discuss volume change for loading in 3 perpendicular directions. E is the dilation or the unit volume change. We earlier found out epsilon x dash. So E is equal to epsilon x dash plus epsilon y dash plus epsilon z dash. Now substituting this expression and the corresponding expressions for epsilon y dash and epsilon z dash, we get this formula. Hydrostatic pressure is a special case of this formula, where all the 3 perpendicular stresses are equal to P. So dilation is given by this expression. P can be given in terms of P and K, where K is the bulk modulus. We notice here that the relationship of shear stress and strain is somewhat analogous to the relationship between axial stress and strain. Also, the treatment in uniaxial direction, where we have found strain and then axial extension, is somewhat analogous to the treatment of loading in 3 direction, where we have found strain and then volume change.